Hi, well, good morning. Welcome to our science seminars. I'd also like to remind you that today at 1:30, there's a special candidate forum for a chemistry position, and that'll be in this room as well, I think. So if you want to come out to see who's interviewing for a chemistry position here at Paterno, come on out for that. It'd be good to have student input on that. Yes? So we want you to come on out for that day. Today, our speaker will be introduced to you by our own Dr. Fernand. Yes? And I will now give her the floor. And let's welcome the introducer to our speaker today.
Dr. DeBoer always makes me laugh, so he has a sense of humor. Anyway, today I would like to introduce Cameron Hartzler. He is forensic chemistry student, a sophomore, and he has been as well my advisee, so it has been an honor to have him. And he will be talking about the research that he did last year in the summer of 2018, together with another student who has graduated now. So at this, I have to say altogether, this has been a research that we did several years, and basically it's coming to an end because the printer stopped working, and as well, like this, all things all together, this is as well my last semester here at Paterno University. So, but anyway, he's finishing strong for us and has some good future suggestions, future studies that basically might, maybe we can work from it further, I myself or he himself or however things goes. But once again, please, he's very enthusiastic in everything what he does, so please welcome Cameron as well.
Well, I know it's already been said to you guys, but good morning, Laterno. Today we're going to talk about meth. Just kidding. Today I'm going to be talking to you about the electrochemical analysis of illicit drugs and development of screen-printed sensor electrodes for the electrochemical analysis of illicit drugs. Yes, I practiced that. And so, first of all, I'm going to give you a little bit of background on this research, why we're doing what we're doing, what equipment we're using, what materials we're using, and basically why we started this research. Then I'm going to follow up with the electrochemical analysis of illicit drugs and all that it entails. Then I'm going to discuss screen printing, which most of you may be familiar with on t-shirts, but we're actually wanting to make electrodes with screen printing. Then I will discuss homemade carbon ink, a little project of mine, and what future work can be done by all of you guys, as well as the wonderful people who helped me along this journey. So, what are we doing in this research? Our main objective of this research was to evaluate the oxidation potential of illicit drugs via electrochemical methods. Why? Most people are familiar with the colorimetric tests of illicit drugs, which basically you drop a little bit of the drug, changes to a certain color if the drug is present, voila. The reason that we want to use electrochemical methods, however, is because colorimetric tests often give false positives. And so someone could be wrongly convicted based solely on a colorimetric test. Electrochemical methods, as I will soon discuss, are pretty much surefire. You will know whether you have a drug or not. Furthermore, we want to develop low-cost and portable electrochemical devices. The reason we want to do this is because the equipment needed for the electrochemical analysis of illicit drugs is often expensive, and it requires a pretty decent time training on the equipment. I still don't understand it fully. And so in summary, the goal of this project is to get the accuracy of the electrochemical method of illicit drug analysis with the portability and ease of use of the colorimetric test. Now, all electrochemical analysis is based off of a redox reaction. Now, for those of you who have or haven't had general chemistry, a redox is short for reduction and oxidation. Reduction is the term for when a reactant decreases in oxidation state or receives electrons. Oxidation is just the opposite, where it goes up in oxidation state and loses electrons. A redox reaction, therefore, is a chemical reaction where the reactants undergo a transfer of electrons and therefore have a change in oxidation state. So, how do we measure this redox reaction? We measure it with the potentiostat. The potentiostat analyzes the oxidation and reduction potentials of the materials by running an electric current through the analytes, or the solution that we're analyzing. And basically what this gives us is each oxidation and reduction rate has a peak, or where it occurs the most quickly. So by analyzing these peaks, basically goes up, down, up, and by analyzing these peaks, we can actually determine what is in our sample, because every single chemical or every single substance that undergoes an oxidation and reduction reaction has a unique peak. There are no real false positives for this because every one is unique. And this is the device that analyzes those peaks. The equipment that we use is called the Bob cell, or Dr. Bob's cell. I assume it was made by Dr. Bob. And basically it is a fancy piece of glassware. But these three things here are the main pieces of our equipment. The electrodes. The platinum working electrode, this right here. The silver chloride reference electrode, this fellow right here. And the platinum counter electrode, this right here. The working electrode is the electrode that actually analyzes the solution. The silver chloride reference electrode is the electrode that provides a guiding point of sorts, so that it has something to compare it to. The platinum counter electrode is there to make sure that nothing goes wrong. Along with these three solid electrodes, you can also have a supporting electrolyte, which basically just helps the reaction to move along. It also can increase the visibility of the peaks, which we like. I'm not going to go through this whole list, but basically, to combine these two, we connect a lot of cords to a lot of places. And one of the cords I was a little irked because it connected to nothing. So, what can we get from these pieces of equipment? Well, there's two techniques or two analyses that we can perform. One is square wave voltammetry, which combines the oxidation and reduction peaks into a single peak, like this. Then cyclic voltammetry, which separates the two. And cyclic voltammetry is a little slower than square wave voltammetry, but it was easier for us to use. So mostly this will deal with the cyclic voltammetry analysis of the illicit drugs. So when using cyclic voltammetry, there are certain parameters that you can modify. And they're listed here: the initial energy, scan limit, final energy, scan rate, and step size. The initial energy is the voltage that we start with. Pretty simple. And that is this value right here. The scan limit is where we actually start scanning for redox peaks, which you can see the little area right here doesn't really have much data points. Then you start getting into the mess. The second scan limit is where you bounce back, per se. So right here. The final energy is where you end up. The scan rate is how often do we scan. So higher scan rate usually gives more detail, but it also slows it down. And as I said before, cyclic voltammetry is often slower than square wave voltammetry. And so we like to keep it at a decent rate. And basically what this means is 20 millivolts, we get a scan. And the step size, I honestly cannot remember what we did with that. All I know is we left it at 2. And so, now let's get to everyone's favorite part, the drugs. The analytes of interest were tetrahydrocannabinol, also known as THC, gamma hydroxybutyrate, GHB, and good old cocaine. So, you may not know what these look like, but here they are. There's GHB, honestly one of the simpler ones now that I think about it. There's good old cocaine and THC, aka marijuana. And so we researched articles that focused on drugs that we could analyze. And so the reason that we picked these 3 is because we actually were able to find articles on these drugs. So the first one that we looked at was THC. And the supporting electrolytes, the chemicals that we put in with the drug to get a better peak reading, were NN-dimethylformamide, that will be important later, and tetrabutyl ammonium tetrafluoroborate, also known as TBAT-FB. When we began to look up these chemicals, we realized that we had a problem. We could not use them. These 2 chemicals are extremely toxic. Like, I'm talking full closed-off fume hood, gloves installed in the window, you ain't touching that stuff. Toxic. DMF not so much, we'll get to that later. But we realized that with our current equipment, we would not be able to perform the electrochemical analysis of THC. So we moved on to GHB. And the article of reference gave us the supporting electrolytes of 0.1 molars phosphoric acid, 0.1 molar perchloric acid, and 0.2 molar sulfuric acid. These are pretty powerful acids, but we could still use them. We have the proper chemical technique, or proper safety techniques. But we had another problem. And thus we were unable to perform this because of the limited available GHB concentration. You see, our school actually does not currently have a drug use license from the DEA, or, well, the DEA. And so we are only allowed to use up to 9.606 millimolars, and the reference in the article gave us an amount of 25 millimolars. And from our research, we learned that lowering the concentration of the analyte gives a lower signal. And in the article of reference, the GHB signal was already pretty low. And so if we cut down the concentration, we would not be able to see it at all. And thus, we are unable to perform the analysis of GHB. But good old cocaine. we found a reference article that used a very low concentration of cocaine, 98 micromolars of cocaine, with very usable supporting electrolytes, 50 millimolar phosphate buffer of pH 9.95, and 100 millimolar KCl. And so we finally found a chemical that we could analyze. And cocaine actually has a expected oxidation peak of around +1 volt, so it's pretty well known where this peak is. So this is the article that we used for reference. Determine the purity of street cocaine samples by square wave voltammetry using modified screen-printed carbon electrodes, SPCEs. And again, they use 98 micromolars of cocaine and 100 millimolars of phosphate buffer in 50 millimolars of potassium chloride. And I might have swapped those numbers. Sorry. But this is what they got for the square wave voltammetry. The supporting electrolytes, this line right here, pH 7, and this is the pH of the buffer. Then you have pH 8, pH 9, and pH 10. And if you all notice, the peak actually becomes a little more clear at higher pHs. So that was one of the things that we wanted to confirm in this research. We didn't honestly get to, because this is our results. No clear oxidation peak whatsoever. And so we were a little bit discouraged by this, and we decided that we needed to do further research and do a little troubleshooting on our equipment. And just to make a point, up to this time, we have not successfully made, up to the time that this analysis was run, we have not made our own screen-printed carbon electrode yet. I'll get to that point later. And so, the first thing that we wanted to do was to troubleshoot. So we started with the reference electrode, the silver-silver chloride one. We realized that looking in the little vial that is our reference electrode, we realized that the sodium chloride solution that was inside of it was low. So our solution was simply to refill the electrode. However, we had a bigger problem. A contaminated frit. The frit is the little piece on the end of the vial that actually is in contact and measures the analyte. And so we looked at it, realized it was dirty, so we decided to find a way to see, okay, just how bad is it? And we found that in the user's manual. And so we ran an interference test and got 277.892 kiloohms of resistance. We read in the manual it should not be more than 1 kiloohm. We had a big problem. And so our solution was to replace the electrode tip, or frit. And thanks to the help of some wonderful people from the engineering department, we were able to succeed in doing so. We ran another test using our new and improved reference electrode. Unfortunately, we got similar results to the first test that you saw. So we had to do a little more research and troubleshooting. So we moved on to the working electrode. And that was when I realized most of the research that we've been doing had been, how shall I say, skipping a minor but important detail. That the platinum working electrode did not give a clear peak for cocaine in our reference article. And so we realized that with our platinum electrode, we couldn't analyze cocaine at all. However, upon further reading of our reference article, the screen-printed carbon electrodes gave a very clear peak. So, our solution? Get to printing. Again, at the time that this troubleshooting was being done, we had not successfully made a screen-printed carbon electrode yet. But I'm going to show you how. The materials that you need are pretty simple. Chromatography paper, a special type of paper used for stuff like this, a wax-printed ink design printed by the Xerox Color Cube 8550 model, and conductive inks. AGCL ink for reference electrode and conductive pads, these things right here, and this little hatch right here. And carbon ink for the working and counter electrode. These two right here. And this stuff is expensive. So we decided to use some paint to test print, if you will. The wells and templates were designed in SolidWorks, thanks to the help of the engineering department. So here you have the wells, you have the template for the silver chloride, you have the carbon, and you have the finished product. So how screen printing works is you have your material that you want to screen print on. You have a mesh-made template that you run paint or other things through, and it actually prints it onto the material, kind of like a stencil. And so, to prepare the meshes for these stencils, the first thing you need to do is tighten the mesh on a hoop, like here, stir the photo emulsion fluid, this stuff right here, and pour a line of photo emulsion fluid on one side of the mesh, then squeegee it at a 45-degree angle across the mesh. Then, this is a step that we added this year. Once you have applied the photo emulsion fluid, you are to retighten the mesh in a dark room. This eliminates any chance of warping or folding or bending in the mesh, and it significantly improved the amount of meshes that we made. And you are to perform this quickly and place in a dark room for at least 3 hours. Overnight is better. The reason that you want to do this is because, as I mentioned, this is photo emulsion fluid. It reacts to light. We do not want it to react to light until we are ready for it to react to light. So, perform quickly and in a dark room. Then, you actually want to expose it to light by placing the template that was made earlier with SolidWorks and expose the desired template under a 100-watt lamp for about 35 minutes. This causes the photo emulsion fluid to harden that has been exposed to light, but the stuff under the templates will not harden. And so it's much easier to remove, and you are to remove those unexposed parts with warm water at a high pressure and allow these to dry. And that is how you make the stencil. Now for the actual wells that we use, these are double printed on 8.5 by 11 pieces of chromatography paper. Double printed to get extra wax on there, but you have to make sure that the wells are aligned correctly, or else you'll mess up your print. Heat each paper sensor on a hot plate at 150 degrees Celsius until the circles have expanded, using the spatulas to ensure that all parts of the paper are heated, and let it cool for 10 minutes, and voila, you have just made the base for a screen-printed carbon electrode. Now, again, I said, then you move on to the test printing, which is similar to the emulsion technique. You apply a line of paint, in our case, because we didn't want to waste the ink. Squeegee it, and your design is now on your medium. Again, this must be lined up with the wells and with each other, or else the sensor will not work. And here we have silver chloride represented by purple, carbon represented by yellow, and remember up to this point that we had not actually successfully made a screen printed carbon electrode with the inks. Well, I'm here to tell you that this year we actually did. And so, following the previous steps, we then applied the silver chloride ink. I actually got a little on me. It's pretty irritating, so make sure to wear standard lab safety gear when using this. Then we baked in an oven in a fume hood for 5 minutes at 130 degrees Celsius. We then applied the carbon ink, baked for 5 minutes at 110 degrees Celsius. And again, this must be done in a fume hood. And so, once we had successfully printed a carbon electrode, we needed to test it out. So, Darlene, my lab partner, did that with 15 microliters of 6 millimolar ferrocyanide, a common chemical used in this type of analyses because it has a well-defined and well-known oxidation peak. The results: scattered data and overload. And to make matters worse, our sensor ripped. We suspected that this was because the alligator clips touched each other because the sensor was so small. And this is often a very common cause of overload. Plus, any of you guys who have handled wires, they are not PVC pipes. They tend to bend back, thus ripping our sensor. So our solution to this was to enlarge the sensor designs, which my lab partner, Darlene, did. And these are the new electrochemical cell designs. The good news is more ink means better conductivity. So we could get a clearer oxidation and reduction peak. Also, we have more space for the alligator clips to clip on without touching each other. The disadvantage, however, is that we had fewer sensors per print. 4 of these versus 30 of the previous ones. Now, with all this going on, Darlene handled it pretty well. I honestly did not. So while she was working on this, I watched YouTube for the next 45 minutes. And there I found a gold nugget that was honestly from God. Do-it-yourself carbon ink. Literally, you are painting wires on a piece of paper. And so the ink recipe that I used and developed is found at this link. And it's non-toxic. It's extremely easy to make. All you need is acetone, graphite, and cigarette filters. All of these materials can be obtained for a very low price. Heck, we even bought, 300 cigarette filters for just like $3. And as I will show later, it works. But not as well as the industrial. And so the process for making this do-it-yourself carbon ink, or DIYCI as I called it, measure out your acetone and graphite, dissolve the cigarette filters in said acetone, add the graphite, stir, we're done. As I said, extremely easy. And so I decided to further develop this by seeing what happens when I changed some of the amounts, like increasing the acetone, increasing the amount of graphite, and increasing the amount of cigarette filters. And I noticed that as I increased the amount of acetone, the ink became less viscous, which is honestly to be expected because you're adding more liquid. As the number of filters increased, the ink became more viscous, and for some reason the glassware was a lot harder to clean. And more graphite is kept in the ink. The cigarette filters are the binding agent between the acetone and the graphite filters. Graphite, sorry. And thus, when the ink settled down, more graphite was actually kept in the ink, and it made it more conductive. as the amount of graphite increased, I didn't observe any noticeable trend. And so, this, let me get the lights for a sec. This is a simple light bulb circuit that we made to test to see whether this stuff would actually work. This is the do-it-yourself carbon ink, by the way, and voila! We have a winner, folks. However, we also performed this on the industrial ink, and it was much brighter than that. So further development needed to be made on this DIY CI. Now, this was all last summer. Here's what I did this summer. I did some more reading, or not this summer, this spring. I did a lot more reading and got a lot more new information. I also had another another semester of organic chemistry. Thank you, Dr. Hathaway. And I also decided that I needed to move on with the idea that we needed to angle the sensors, an idea that we had last summer. And as Dr. Fernand mentioned at the beginning of this talk, I will be speaking on to why this is the last term of the electrochemical analysis of illicit drugs. So, some of the new information that I got. Dimethylformamide, the chemical that I mentioned earlier, wasn't as toxic as previously thought. As I further read on the safety data sheet, I realized that we actually could use this with standard lab safety gear, long sleeves, gloves that reach past the wrist, goggles, and a fume hood. So long as you keep it in the fume hood, you're good to use it. Also, I found out that I was not the first one to attempt do-it-yourself homemade carbon ink. And I found a pretty good recipe in an article that requires 1.8 grams of ONPOE, 5 grams of 8% PVC solution, the same PVC that's in PVC pipes, and 3 grams of carbon powder. And I also found something interesting. One of the things that we wanted to do was to modify our screen-printed carbon electrodes, and to do that, we needed to have nanomaterials dispersed in a medium. Dimethylformamide was that medium, but I also found that dish soap can be used for nanomaterial dispersion. And I found that kind of interesting because of the whole DIY theme that we were going for, and so I decided to carry forward with that. But first, we had to fix the sensors. And so, I found out that Darlene had actually already angled the sensors. And so, I was left with the task of transferring the file into the correct format. That took about 2+ hours. It was not an easy task. So, we had successfully transferred the files, and I went to print them. The printer that we used to print the sensors and the well template died. And when we attempted to troubleshoot and perform maintenance, we found that it would be too expensive to fix, and the model that we were using is no longer in production. Thus, we are kind of at a standstill. However, there are still things that need to be done in this research field, and that's why I wanted to talk to you guys about it. Though I may not be able to perform this research anymore, and Dr. Fernand is leaving after the semester. Again, there's still stuff that could be done, which brings me to future work proposals. The first thing that we need to do is test the enlarged sensors, and this has to be done before anything else because if we don't have a working sensor, then we can't work on the sensor, if that makes any sense. Basically, you have to have the foundation before you can add to that foundation. The sensor is our foundation. Then, I wanted to test the homemade sensors based on the O and POE. I first mispronounced as oh nope. With the 1.8 grams of 2-nitrophenyl octyl ether, 5 grams of 8% PVC solution, and 3 grams of carbon powder. Apparently this is less expensive than the industrially prepared inks. The good thing about this is that it has already been tested and it works very well. We just haven't tested it on paper yet. So that's one of the things that I want to leave open. Then I would like for future research to be made with the do-it-yourself carbon ink. As mentioned before, it's extremely inexpensive and very easy to make. However, we were not actually able to test a sensor with the DIY CI, and as I said before, it's not near as conductive as the industrial ink, so further development will have to be made on that. Then, again, disperse multi-walled carbon nanotubes in dish soap to modify the working electrode. And the thing about modifying the working electrode, you basically have two steps: dispersion and deposition. Dispersion is where you basically disperse the nanomaterials in a solvent, and then the deposition is where you use said solvent to place the nanomaterials on the sensor. The dish soap has been evidenced to disperse the materials, but as to how we are going to deposit the materials, we honestly don't know. Dimethylformamide, or DMF, the article that we had a very easy procedure to deposit the materials, but dispersing the nanomaterials is the more difficult task. Even though DMF was not as toxic as previously thought, the dispersion of nanomaterials in DMF requires equipment that is quite expensive, in the multi-$1,000 range. However, we actually do have one of the pieces of equipment prescribed by the article, and according to a well-known and well-loved professor here, you pretty much only need the piece of equipment that we have, but it might take longer and it might not work, so we're still leaving that up in the air. And finally, this was a little idea that I had at the beginning of our research time, was to run cyclic voltammetry on cocaine in urine. Basically, when I read that cocaine and its metabolite dissolved in urine, I assumed that there was a dissociation of ions. This dissociation of ions creates an electric current, which then can be analyzed. Unfortunately, we were not able to carry on with this idea, but I'd kind of like to see what happens with it and develop urine as a supporting electrolyte. And with that, I would like to thank all the people who were involved. Dr. Vivian Fernandez, my advisor, wonderful teacher, and research faculty sponsor. My lab partner, Darlene Ishimwe, that's her right here. And I'd also like to thank the Laterno 2018 summer research team as a whole. They were very helpful in encouraging me and helping me with some things that I had not yet learned. I'd also like to thank Reed Phillips, who helped us fix our reference electrode, Mr. Jeff Johnson, who helped me get the SolidWorks file in the right format, Dr. Howard Henry, who provided us with the appropriate materials needed for our circuit test, Dr. Hathaway for providing general good advice and teaching me some chemistry that I had yet to learn. I'd also like to thank Laterno University as a whole for just being a great place where God works in so many ways. And finally, I'd like to thank the Welch Foundation for providing the funding for this research. Thank you very much.
Are there any questions?
So what exactly is the secret ingredient hiding inside of cigarette butts that allows you to use it to make carbonic?
If I remember correctly, it might have been cellulose acetate.
It's carbon. Carbon is in there.
I could be wrong, it's been a while.
It's cellulose.
Anyone else?
You mentioned using the soap to disperse multi-walled carbon nanotubes, and though I've heard of nanotubes, how do you have a multi-walled tube? I was curious about that.
I will use the for that. Poking down the edge, a single ring of carbon nanotubes, or a single carbon nanotube enclosed by another carbon nanotube.
And what advantage does that have to single-walled nanotubes in your research?
Mostly because that's what the article used, and multi-walled carbon nanotubes seem to have better track record with modifying the working electrode, so that's why we chose to use the multi-walled instead of the single-walled.
And you mentioned that the DMF something
Dimethyl-formamide?
yeah, it was you were supposed to do research on something that got turned down because of something like it was too toxic. And then it's
The
what was
THC.
it? The THC marijuana? Okay, just I was wondering how you could have thought of it better. Maybe feature research on it or something with it.
Well, the TBAT FB is, again, extremely toxic, so until we get some better safety equipment, we here at Laterno will not be able to work with that chemical. Anybody else? Feel free to ask. There are no stupid questions. And if there were, I would ask a ton of them.
No questions? Well, let's thank once again Cameron. You're invited to join us in the Joyce Room in case you may have one-on-one questions for Cameron, and Dr. DeBoer will be as well there. So please come on.
Don't log out yet,
What?
Don't log
log
out.
out.
You said it right as I was doing.
Well, we just lost it then. You lost the folder.
Lost the video.
Yeah, turn it back on. Log back in.
Log in back.
Thank you.
And then start up Doceri again.
I've had so many situations where that happens, where someone tells me do not do something.
Where's the series?
There you go. He knows where it is.
Literally, that has happened so many times where someone tells me not to do something. The
All right.
millisecond
Now
that I'm
don't
doing
log out until they tell you you
that
can.
I'm doing
Okay.
it, and my